Welcome to today's podcast. My name is Henry Omale, and today we're looking at A-level physics, and our topic of discussion is Kirchhoff's law. So at the end of this class, we are expected to be able to understand Kirchhoff's first and second laws and how to apply these laws in solving circuit problems, and then finally would explore some real-life applications of Kirchhoff's law in electrical engineering and electronics. Now, an introduction to Kirchhoff's law. Kirchhoff's laws are fundamental rules we use for analyzing circuits, and they are based on the laws of conservation of charge and energy. Remember that the law of conservation of energy states that we can neither create nor destroy energy, but we can transform it from one particular form to another, meaning that the overall energy within the system remains unchanged. The same thing applies to charges, and we'll see how this law, Kirchhoff's laws, addresses this when it comes to energy and charges. And then Kirchhoff's laws are essential for solving complex circuits that cannot be simplified using the normal series and then parallel rules alone. There's a misconception that I found out that many students have that Kirchhoff's laws are used for analyzing simple circuits, but no, they are also vital when we want to analyze complex circuits. So we'll be looking at the first law of that's the first Kirchhoff's first law, and this is also called Kirchhoff current law, or we can also call it Kirchhoff nodal law. So we'll be looking at the statement of the law and its mathematical form, and then why this law applies. So to state the law states that the total current entering a junction equals the total current leaving the junction. So when you have a circuit and you have a node or a junction in that circuit, like a kind of branch or branches, the total current entering a particular branch is equal to the total current leaving it. So in mathematical form, it means that the algebraic sum of current entering a node plus the algebraic sum of current leaving the node is equal to 0. So current is one of those scalar quantities that also have direction. We'll come to that later, and as we progress, you will understand better. So we are saying that the total current entering a node is equal to the total current leaving it invariably. The total current entering a node is equal to total current leaving it. So that is the mathematical representation, and why this is so is because, like we said before, charges are conserved. There is conservation of charges within that point. So this is what happens. This is what Kirchhoff's law, current law, tries to explain. If we look at this diagram, you would see that we have a node here, and based on this node, we could see that we have some current. We have current I1, we have current I2, current I3, and current I4. So what Kirchhoff's current law is basically telling us to do is that we should look at how many of which of these currents is entering this node, and which of these currents is or are leaving the node. So in this case, we can see that only I1 is going into this node, and then when it gets to this node, I1 branches into 3 other currents. We have I2, we have I3, and then we have I4. So based on Kirchhoff's current law, it is just basically telling us that I1 is equal to the sum of I2 and then I3 and I4. So I1 plus I is equal to I2 plus I3 plus I4. Now let us look at some misconceptions that Kirchhoff's first law or Kirchhoff's current law tries to debunk. First of all, I found out that many students have a misconception that current gets used up within a circuit. Students think that electrons are used up by components, but this is not true. Like we said, Kirchhoff's law tells us that current is conserved. In reality, current is conserved as the number of electrons entering the component equals those leaving it. Second misconception that students have is that current is always the same. That current is the same everywhere within a circuit. Yes, while this is true for series circuits, it is not so for parallel circuits and even for complex ones. So to debunk this misconception, Kirchhoff's law tells us that current divides at nodes, it divides at junctions according to the resistance present within that branch where it is dividing to. So this is what Kirchhoff's law tries to help us to explain. So Kirchhoff's law helps us to debunk these misconceptions. So now that we've gotten that out of the way, let us use our previous diagram to solve an example. So let's look at this diagram and then the question attached to it. It says if I1 is equal to 10 amps, and then we have that I2 is equal to 3 amps, and then I3 and I4 are equal, that we should find the value or the values of I3 and I4. So to solve this, based on what Kirchhoff's law tells us, that the sum of current entering this node equals to the sum of current leaving it, and we've already written we've already written the formula before. We're going to still write that formula again, that I1 is equal to I2 plus I3 plus I4. So the solution, we say that according to Kirchhoff's current law, the algebraic sum of currents in a node is equal to 0, which means that as we see, I1 entering this node, and then I2 going out, I3 going out, I4 also going out, means that I1, which is entering, is equal to the sum of I2, I3 and I4. But then before we begin to do substitutions, there is also a point to note from the question. The question says that I3 and then I4 are equal. So I would like to represent I3 and I4 as an equal current by using the same notation to depict them. Remember, we said that I3 is equal to I4, and I want to use capital letter I to represent them. So anywhere I see I3, I put big I. Anywhere I see I4, I also put big letter I. So after having gotten that out of the way, we can go ahead and do some substitutions where we have I1 is equal to 10, we put I2 is equal to 3 amps, and then we put I3 equal to big I, and then I4 also equal to big I. So in doing that, we now have 10 is equal to 3 plus I, and we can resolve this equation to have 10 is equal to 3 plus 2I. So if we are going to rearrange this equation, we can move 3 over to the other side, and this becomes minus. Positive 3 becomes 10 minus 3. So we have that 2I is equal to 10 minus 3. And in resolving that, meaning that 2I is equal to 7. And then I, by dividing both sides by 2, we have that I is equal to 3.5 amps, meaning that I3 is equal to I4 is equal to, and both of them are equal to 3.5 amps. So we can see that Kirchhoff's nodal law or current law has helped us to resolve to know the values of currents entering into this node, and then the values of current leaving the node. And if we want to do a check, we can see that 3.5 times 2 is equal to 7. That's 3.5 times 2 is equal to 7, and that's the sum of I3 and I4 is equal to 7, but I2 is equal to 3, so 7 plus 3 is 10. You see, 10 amps entered into this node, and 10 amps left the node. So that is a check to see that Kirchhoff's current law was followed. So let's look at Kirchhoff's second law, or Kirchhoff's voltage law. From Kirchhoff's second law, we'll look at the statement. Again, we'll look at the mathematical form and then why this law applies. So what does it state? Kirchhoff's second law of voltage law, or you can also call that loop law, states that the total voltage around a closed loop in a circuit is equal to 0. Remember, the current law addresses current entering a node, but Kirchhoff's voltage law addresses voltages within a closed loop of the circuit. So let us look at the mathematical representation of that. We have that the summation of voltages within a closed loop is equal to 0. And then why this is so is because energy is conserved. Again, remember, in the case of Kirchhoff's first law, we said that charges were conserved. Now we are saying in Kirchhoff's second law, it is energy that is conserved. So energy within a closed loop or around a loop is conserved. So let's look at an example of how to use Kirchhoff voltage law, a simple example. And in the example, it says that an 18-volt battery causes 4 amps of current to flow into the circuit below. And we have the circuit below. You can see that as according to the question, we have an 18-volt battery, and then we have a 4-amp current flowing across 3 resistors, 1 ohm, 3 ohms, and then R3. So the question is that we want to find the value of R3 using Kirchhoff's voltage law or loop law. So one thing of particular interest is the fact that we have what we call voltage drops across circuits. When we have series circuits, as this case is, we know that the same current flows through the circuit, and for this circuit I would like to assume that the direction of the flow of current is according to what was drawn for us here in the question. You can see they gave us a direction for the current, so we want to follow that same clockwise direction here. So we have a clockwise flow in this case. So in a series circuit, we say that the same current passes through all the resistors. Now, one particular thing of interest is the fact that when we have a series circuit, we have what we call voltage drop across resistors. Like in this particular circuit, we have a 4-amp resistor crossing the 1 ohm, a 4-amp current, passing a 1 ohm resistor, meaning that the voltage drop across this 1 ohm resistor is equal to 4 times 1. Then there's also another voltage drop across the 3 ohm resistor, which is given by the current times the value of the resistance, which is 4 times 3. Remember that voltage is a product of current and resistance. So the voltage drop across the 1 ohm resistor is 4 times 1. The voltage drop across the 3 ohm resistor is 4 times 3. And the voltage drop across the R3 resistor is 4R3, or 4 times R3. So we are saying that if you sum up all this voltage drop across the resistors, it's supposed to be equal to 18 volts. That is basically what Kirchhoff's voltage law is saying. So using Kirchhoff's voltage law, we will have that 18 will be equal to 4 times 1 plus 4 times 3 plus 4 times R3. So all these sum of products, which gives us voltage drop across each of the resistors, should be equal to 18. So if we are going to further rearrange our equation, we'll now have that 18 is going to be equal to 4 plus 4 times 3 is 12, which is going to be 16 plus 4r3. So we have that 18 is equal to 4 plus 12 plus 4r3, and this is equal to 16 plus 4r3. So if I'm going to move 16 over the equal to sign to meet 18, I can rearrange this equation to become 4r3 is equal to 18 minus 16, which is equal to 2. So we have 4r3 is equal to 18 minus 16 equal to 2. So if 4r3 is equal to 2, we can just divide both the left hand side and the right hand side by 4, and we'll now have that r3 will be equal to 0.5 ohms. So we can see that we've easily used Kirchhoff's second law to find the value of R3. Before we proceed to solving more difficult problems, I would like us to, first of all, like we did for the current law, to debunk some misconceptions that students have when it comes to voltages. So the first misconception, that students have concerning voltage is that voltage is the same everywhere. And this is not true. Just like the same misconception they had concerning about current, the same misconception comes up again for voltages. It is not true, because in reality, voltage drop, what we call voltage drop across resistors, and this happens when we have resistors connected in series to components. So we have voltage drop across resistors and other components, and the total voltage drop around a loop equals the total EMF supplied. As we could see from the example that we just saw, the total voltage drop across those components, across each of the resistors, as the case was, it was equal to the voltage supplied within that loop. Now, another misconception that students have is that you can just add voltages without considering direction. No, this is not so. You have to, any convention you take, like in the case we solved just now, we used a clockwise direction to depict the flow of current and the flow of voltage, the movement of the voltage. So where we have a closed loop, we said voltage rises and drops. So it rises from batteries, that voltage comes up from batteries and drops across components like resistors. In this case, it drops across resistors, and then this must be accounted for with correct sign conventions. So what I do, what I advise you to do is that whenever you see a battery, you can give it a positive voltage, especially when the battery is supplying, is the one supplying the voltage in the circuit. So its voltage there is positive. Then when we have the voltage, the current from the battery coming across a resistor, is what we have. We have what we call a voltage drop across that resistor. So that's what happens when we are doing calculations. So we have to consider the direction of the voltage, and then we also like to debunk the fact that some students believe that the laws that we are using, these Kirchhoff laws, does not help to break down or complex circuits, or the law fails when we want to break down complex AC circuits and all that. No, Kirchhoff laws are universal for both DC and AC circuits. In fact, when we come to the applications of Kirchhoff law, you will see how you use it for more complex circuits to derive the overall circuit for either a medical equipment and all that. So the law is a universal law that applies to all circuits, no matter how simple or complex they may be. So let us look at how to solve circuit problems using Kirchhoff's current law and Kirchhoff voltage law. So the first thing we usually do is to assign directions. We assign directions like we did, assign direction to the flow of current within the circuit. Then we apply Kirchhoff's current law at the junctions, at the nodes of that circuit, and we apply Kirchhoff voltage law around the circuit's loops, and then we set up some simultaneous equations, and we resolve those simultaneous equations either using substitution method or matrix method. For this class, we'll be looking at using substitution method. I hope that I have the chance to do a matrix method. We use matrix method mainly. I like using matrix method mainly if we have more than two unknown, like 3 variables that we're solving for. Then I prefer to use matrix method. But for this case, we'll be using simultaneous substitution method to solve our simultaneous equation. So a tip for us before we proceed is that a wrong direction, if you depict is a wrong direction for your current, that it will only result in giving you a negative value of the current. So that is not a problem. Anytime you use a direction, you maybe current was probably flowing in a clockwise direction, or the current was moving down a branch and not up, and you gave a convention that it was wrong. What will happen is that you gave a direction that was wrong. What will only happen is that you would get a negative value of your current, which shows that the actual direction of that current is in the opposite direction. So let us take this tip. A wrong direction guess will just result in a negative current value, but the value of the current in terms of magnitude would be the same. So let us look at a problem. Example says, use Kirchhoff's voltage law to find the value of I in the circuit below. So in our circuit, we have a circuit with 2 loops, and then in our circuit we have a battery, a 30 volts battery, having an internal resistance of 0.4 ohms, supplying current I to a 5 ohm resistor. So this 5 ohm resistor is in series to another parallel resistor combination. This 3 ohm resistor is in parallel to the 7 ohm resistor, and their combination is now in series to the 5 ohm resistor and the internal resistance. So in this question, we have 2 loops, and I would like to use a clockwise direction for the flow of current. We have 2 loops. This one, we have use clockwise direction for each of the loop. The first loop here, and then the second loop. So the first loop I'll call loop 1, and the second one I will call loop 2. So for loop 1, we have current. Let me say the current flowing in loop 1. Let me call it I1. Say I is equal to I1. That's the current flowing in this loop. I want to just call it I1, and we know that I1 is going to be equal to I. So the current flowing in loop 2, I want to call it I2. So I1 is equal to this current here, I, and then I2 is the current flowing in loop 2. So that is what we're going to be using Kirchhoff's voltage law to resolve. So the algebraic sum of voltages in loop 1 is equal to 0, as given by Kirchhoff's voltage law. The algebraic sum of voltages in loop 1 is equal to 0. So which means that like we said before, when we talked about voltage drop, we have a voltage drop across the battery as a result of the internal resistance. Then we have a voltage drop across the 5 ohm resistor as a result of the 5 ohm resistor. Then we have a voltage drop across the 7 ohm resistor. So we are moving in a clockwise direction from like this. It goes to the 5 ohm resistor. We have a voltage drop there. Then we come down to the 7 ohm resistor. We have another voltage drop here. It comes up to this battery. we have a voltage drop across the battery as a result of internal resistance. So let us put that in mathematical form. We would have that 30 minus, so I'm saying that anywhere we have a voltage drop, let us use a minus sign. I would have just taken this one to over the equal to, and this would have been positive, but I want to use a minus sign to depict voltage drop. So 30 minus what is the voltage drop across the consider that this 0.4 ohms and these 5 ohm batteries 5 ohm resistor are in series. We can consider that the 0.4 ohms internal resistance and this 0.5 ohm resistor are in series. So when we have series resistance, we add. So we say 0.4 plus 0.5, and then the current that flowed through them, we said it was I1. Remember that I1 is equal to I. That's what I want to use. So that is the voltage drop across the 5 ohm and internal resistance resistance. That's the voltage drop across them. So the voltage drop across the 5 ohm resistor and internal resistance of the battery. So minus the voltage drop across the 7 ohm resistor. Now this is where things get interesting. We say voltage drop for each of the resistor is equal to the product of the value of the resistor and the current across the resistor. So that's why we said voltage drop across this 5 ohm resistor is actually 5 times I1, and voltage drop across the internal as a result of the battery's internal resistance is 0.4 times I1 also. So we only just combine that to get 0.4 plus 5 times I1. But when it comes to this 7 ohm resistor, we can see that it's a branch. We have a branch here. You can see that it's a branch here. We have a node here, and it is not only I1 that goes through this 7 ohm resistor. I1 is moving in a clockwise direction across the 5 ohm resistor and then across the 7 ohm resistor. It goes down the 7 ohm resistor like that. In the same vein, in this loop 2, we have I2 there. As I1 is trying to come down the 7 ohm resistor, I2 is going up the 7 ohm resistor. So there's like a kind of cancelling out. So the current across the 7 ohm resistor is actually this the summation of current across them. That's the summation of the I1 and I2. I1 is coming down, I2 is going up. So I'm using that current coming down is positive and then current going up is negative. Again, like I said earlier, current is one of the scalar quantities that we have that has direction, but it's not a vector quantity in the sense that the summation of current doesn't follow vector summation. So in this case, we have I1 coming down, I2 going up. So the current across the 7 ohm resistor is I1 minus I2. So meaning that the voltage drop across this 7 ohm resistor is 7 times I1 minus I2. So 7 into bracket I1 minus I2 will give us the voltage drop here. And again, we have a negative sign, minus 7, because of the voltage drop. So this will be equal to 0. That's 30 minus 5.4 I1 minus minus 7 times I1 will give us minus 7 I1 plus, because we have minus 7 times minus I2 will become plus I2 is equal to 0. You can resolve this further to get that this minus 5.4 I1 minus 7 I1 will give us minus 12.4 I1 plus 7I2. So I would like to rearrange this equation to become 30 is equal to 12.4 I1 minus 7I2. That's because when this negative sign crosses the equal to sign, it becomes positive, and when the positive crosses to the right hand side also, it becomes negative. So I can call this one equation 1. To go further, we could look at the second loop 2, and in this loop 2 we see that we've taken also a clockwise direction for the flow of the current, clockwise direction, and we call that current I2. So the sum of again, it says the sum of voltages in loop 2 is equal to 0, meaning that if we take the sum of voltage drop across this resistor, if we take the sum of voltage drop across these resistors in loop 2, it will be equal to 0. That's the algebraic sum of the voltages across the resistors in loop 2 will give us 0. The same way we took the convention, said 7 I1 minus I2, 7 into bracket I1 minus I2 is the voltage drop across the 7 ohm resistor. We still maintain that convention here. So we have that the voltage drop across this loop would be 7 I1 minus I2 which is equal to I2 times 3. So if we arrange that, we have that 7 into bracket I2 minus I1 plus 3 I2 is equal to 0. Remember, it was supposed to be 7 into bracket I1 minus I2. I1 minus I2 is equal to I3. So if I move this, if I move it across, I can change I1 minus I2 to become I2 minus I1. So it becomes 7 into bracket I2 minus I1 plus 3I2 is equal to 0. It's the same thing, just only changed the signs. So this is equal to 0. We can resolve this further to have that 7I2 by expanding the bracket. We have that 7I2 plus 3I2 collecting like terms minus 7I1 is equal to 0. 7I2 plus 3I2 will give us 10I2, and then minus 7I1 is equal to 0. We can call this one equation 2. So from equation 2, we can see that I2 is equal to 7 over 10 I1, which is the same thing as 0.7 I1. So what we are going to do now is to substitute using anywhere we see I2, we put 0.7 I1. So by substitution, we say substitute into equation 1 this value. Anywhere we see I2, represent it with 0.7 I1. So if we are going to put that into equation 1 here, it will be that 30 is equal to 12.4 I1 minus 7 into bracket 0.7 I1. So that will give us this. 30 is equal to 12.4 I1 minus 7 into bracket 0.7 I1. If we resolve this further, we'll get that 30 is equal to 12.4 I1 minus 4.9 I1. And resolving that further gives us I1 equals to 4 amps. So remember that I1 is the same thing with I. So I1 is equal to I equal to 4 amps. So I don't know, in the same vein, if we can can you attempt using the same method to solve for I2? Can you try to use the same method to solve for I2? So let's proceed. We've used Kirchhoff's voltage law to solve for I in this case. We'll do the same thing now using Kirchhoff's current law. And based on Kirchhoff's current law, it says that the algebraic sum of current entering a node is equal to 0. The algebraic sum of current entering a node is equal to 0. And we can see that we've been given the convention for the flow of current. Current is moving into this 5 ohms battery, coming to this node, and then we can see the current leaving, coming back to the battery. This is the direction of the current that they've used, the conventional flow of current that they've given to us. So move from the positive side of the battery, comes to the 5 ohm resistor, and then the 5 ohm resistor and the internal resistance of this battery are in series, and both of them are also in series to the remainder of this circuit. Then the 7 ohm resistor is in parallel to the 3 ohm resistor, but their combination is in series to the rest of the circuit. So you can see this I1 passes through this 5 ohm resistor and gets to the node. It enters the node, and when it gets to the node, it splits into two. It splits into two, I3 and I2. I2 coming down and I3 going to I2 coming down the 7 ohm resistor, and I3 coming down the 3 ohm resistor. So we can see, based on Kirchhoff's nodal law or current law, that I, which is the current entering here, is equal to I2 plus I3. So based on that, we can have our equation 1, say that I is equal to I2 plus I3. That is based on Kirchhoff's law, his current law. So we can call that equation 1. Current entering the node equal to current leaving it. So I is equal to I2 plus I3. So to go further, we can see that in the previous example, we talked about voltage drop. Voltage drop applies whenever we have series combinations, whenever we have series circuits. So there's a voltage drop across the battery as a result of the 0.4 ohm internal resistance, and there's a voltage drop in the circuit as a result of the 5 ohm resistor. But when the voltage comes after this voltage drop, when the voltage gets to this node, you can see that we've written the letter V there, meaning that the same voltage will pass through this 7 ohm resistor and this 3 ohm resistor, because they are in parallel. Let's not forget, the same voltage passes through through components, or through resistors, through resistors that are connected in parallel. The same voltage passes through them, but there is a voltage drop whenever we have a series resistor. But in terms of current, the same current passes through resistors in series, but that's not the case for current when the resistors are connected in parallel. There's a split. As you can see, the current splits into two here. When it comes to this parallel circuit, it splits into I2 and I3, but the same voltage passed through the node. This node here, the same voltage is present here, going through the 7 ohm resistor, and then going through the 3 ohm resistor. So to proceed, we have this this is the equation that we can derive from that. So I'm going to explain how I came about this equation. Now, I talked about voltage drop. Voltage drop applies when we have series. So the voltage drop from this battery to this node, the voltage drop from this battery to this node is given by 30 minus V. Remember, we're trying to resolve. We've said that I is equal to I2 plus I3. So what is I? I is equal to the current I is equal to the voltage, the sum of voltage drop across the across this resistor and the internal resistance divided by the series combination. So I is equal to 30, the voltage drop across here. If you call the voltage at this node, let's pick that the voltage at this node is V. If we say the voltage by this node is V, then the voltage drop across the 5 ohm resistor and based on the internal resistance of the battery will be equal to 30 minus V. That's the voltage drop. So if we divide it by the series combination of the resistance of this 5 ohm of this resistor and internal resistance, we would have the current I. So the current I is equal to 30 minus V divided by 5 plus 4, which is the series combination. So that will give us I. Now what is I2? I2 is going to be equal to the current that passes through the 7 ohm resistor, and that is going to be equal to V divided by 7. That's I2. Plus, what is I3? I3 now, the same voltage will pass through the 3 ohm resistor. So I3 is going to be V over 3, will give us the current I3. So now that we've established that, we can resolve this fractions to get a more workable equation. So 5 plus 4 is 5.4. So we have that 30 minus V over 5.4 is equal to V over 7 plus V over 3. If I want to resolve the right hand side, let me resolve this right hand side by getting the LCM. The LCM of 7 and 3 is 21. So I can multiply. I can resolve this one further. That's V over 7 plus V over 3. I can resolve that further to have 30 minus V over 5.4 is equal to look for the LCM. We have 21, and then 7 into 21 is 3 volts, and 3 into 21 is 7 volts. So if I add 3 plus 7, we have 10 volts. So this is equal to 10 volts of 10V over 21, not 10 volts, sorry, 10V based on the value, the V. We use V to depict the voltage there. So we have 10V over 21. So 30 minus V over 5.4 is equal to 10V over 21. And if we resolve this further by cross multiplying, we'd have that 21 into bracket 30 minus V is equal to 5.4 into bracket 10V. Resolving that further, we have that 630 minus 21V is equal to 54V. So V now will be equal to 630 divided by 75, and that will give us 8.4 volts. So if V is 8.4 volts, what is the current that passed through the 5 ohm resistor? Remember, from our equation 1, we said that I is equal to 30 minus V over 5.4. So if we take this value of V and put it into the left hand side of equation 1 and 2, would have that I is equal to 30 minus V over 5.4. 30 minus V over 5.4, that's what I is equal to. So I now will be equal to 30 minus 8.4 over 5.4. That would be 21.6 over 5.4. So that I will be equal to 4 amps. So we can see that we've still gotten the same 4 amps we got at when we use Kirchhoff's current law. The same value we've gotten now using when we did Kirchhoff's voltage law, sorry, the same value we've gotten now using Kirchhoff's current law. So in the same vein, can you attempt using the same method to solve for I3? To solve for I3 and even I2 as the case may be. So let's try to attempt that and see what you come of laws. How does Kirchhoff's law apply to real life? Number one, if we look at electrical grid management, in balancing supply and demand in networks, which comes in handy when we talk about generation, transmission, and then distribution of power. You know, before we begin to distribute power, it is good to do what we call a feasibility study to know the amount of power that is required by a particular locality, for instance. So through Kirchhoff's law, we are able to know how to balance supply and demand within the network of the grid, within the supply of the national grid. And then we also use Kirchhoff's law in electronic circuit design. Like we said before, Kirchhoff's law does not only apply to simple circuits, it also applies to complex circuits. So we use it to design circuits in terms of whether you talk about electronics, in terms of radios, in terms of television. Those when you open your TVs, you will see some what they call them. You see some circuit boards. All the circuit boards were designed using Kirchhoff's law. Also, medical devices for safe power delivery and equipment, like in ECGs, we use Kirchhoff's law to design those medical devices to make sure that we do not use higher than necessary voltage or current within the device, so that it doesn't cause harm to people. And in the same vein, like we talked about the electrical grid management, we also use Kirchhoff's law to manage smart grids within the locality, such that when power is needed, so that we don't exceed them, the maximum demands that we need to within a locality or within national grid. And then it's also used for space and aeronautics circuits. We see all these crafts, even in our cars and vehicles. We have electrical parts of them. So Kirchhoff's law helps us to know the correct size of battery to use, and then how the components that we use with those battery without necessarily causing harm to the vehicle. So we use Kirchhoff's law in design of circuits generally, no matter how simple or how complex the circuits may be. So in summary, we said Kirchhoff's laws are based on conservation principles. We talked about the conservation of charges for the current laws, and we talked about the conservation of energy for the voltage laws. The current law has to do with charge conservation at junctions, and then the Kirchhoff's voltage law has to do with conservation of energy around the loops, and they are critical in designing, testing, and understanding circuits. And we have a wide range of application of Kirchhoff's law in the use of in its use for designing smartphones to designing satellites. So I would like us to now go ahead and check our understanding so far with what we've learned. What does Kirchhoff's first law state? What does Kirchhoff's first law state? And remember, Kirchhoff's first law has to do with the Kirchhoff's current law, which states that the sum or the algebraic sum of current in a node or in a junction is equal to 0, meaning that the sum of current entering a node is equal to the sum of current leaving it. That's Kirchhoff's first law. Now, the second question says, What's the total voltage in a closed loop? What's the total voltage in a closed loop? Okay, the total voltage in a closed loop is equal to what? 0. The algebraic sum of total of voltage in a closed loop is what? Is 0. Meaning that the voltage supplied is equal to the voltage drop. The voltage supply is equal to the voltage drop. Voltage supply is equal to the voltage drop. So as the voltage within a closed loop remains constant. So that is Kirchhoff's second law. Now the third question says, name one real application of these laws. And when we're talking about our summary, we talked about application in making smartphones, in the grid, national grid, and analyzing complex circuits. So what happens if you assume a wrong current direction? We said our answer will come out negative, but the magnitude will still be the same. Thank you.